All right, I'd like to work through some titration problems, just kind of go through a few examples that I've picked from the assignment here that will show you a few of the different variations in titration problems. There's really not a lot of variety to them. The biggest thing to be able to do in solving these titration problems is to come up with the equation for the reaction that's going on in these neutralization reactions. Keep in mind that every titration, as you see right away here in number one, is a neutralization reaction between an acid and a base. It's a reaction, you see here, but it specifically is a neutralization between an acid and a base. And the good news is all those equations basically look about the same, so that you don't really have to write a lot of complicated equations. You don't have to write names for things, but we need those ratios of the acid to the base. We need to know if the acid to base ratio is 1-to-1 or 2-to-1 or 3-to-1 or what the ratio is, because that's going to come into play as we do the calculations, the stoichiometry as it is, really for the calculations with the base and an acid in a titration problem. So we've got to have an equation to show the acid and the base reacting with each other. And hopefully you caught here in the last video that an acid and a base will always give us the same overall result. An acid and a base will always react to form the same two products, water and a salt of some kind. I'm just going to put salt here. Salt is a very generic term in chemistry. It's more than just like the salt you'd put on food or mix into recipes. Salt here in chemistry is really any compound formed by the neutralization of an acid with a base. And it's most any ionic compound at all can be called a salt. But we need that equation to be filled in for each of these problems. So I'm going to work with you on number one first of all. On number one, it tells us that we're reacting an acid, HNO3, with a base, NaOH. And remember, bases will pretty much always end in something OH. And acids will always be hydrogen at the beginning, followed by something behind. So you'll have acids with the formula H in the front, and bases with the formulas that have OH at the end. And when these get together, they'll always make water, and they'll always make salt. And if we need to be able to look at the compounds here, the acid and the base, and find the first part of the base and the second part of the acid, and put those together like so, okay, the idea. And in the video you watched here a few minutes ago, hopefully, or the video you've already seen from the Khan Academy, they sort of introduced here that the ions involved in the acid and the base and their charges are important to come across the other side because the positives and negatives swap. All right, and we saw that with double replacement reactions earlier in the year. Here's our equation, and it's balanced with a 1-to-1-to-1-to-1 ratio. And most important ratios within that are the one on the acid and the one on the base. We need to know the ratio of acid to base, and here it's a 1-to-1 ratio. That's really important in helping us answer the rest of this question because there's going to come a step in the stoichiometry where we need that ratio, that 1-to-1 ratio. We don't even really care so much about the product side of this reaction because these questions won't ask you to use the water or the salt, but we need to know the ratio on the left side of the reaction of how they're going to work together. One acid for every base, or is it a 2-to-1 or a 3-to-1 ratio? So to solve this now, we're going to start with the thing that we know about. And it tells us right away the known concentration of NaOH is 0.500 molarity, or moles per liter. And it's going to end on the unknown. What is the concentration of the nitric acid? We're going to need to start with the thing that we know about. We know about the NaOH. So to start our problem, and these calculations will follow the same pattern basically every time. To start our calculation, we're going to start with the volume of the known thing. We know that we have 30 milliliters of NaOH being used. 30 milliliters of NaOH. We need to get into liters. Working in liters is important because all of our volumes will have to match up with all of our molarities, and those are in moles per liter. So the easiest way to think about that. A basic metric conversion is that 1 liter is 1,000 milliliters. And that's 1 liter of NaOH, right? So the question then is, what comes next? Well, that's where this molarity is going to come in. That 0.500 m that we see there given at the beginning is, for every time you see this m, it's moles per 1 liter. Moles of NaOH per 1 liter. So when I see 0.500 molarity, that means there are 0.500 moles of NaOH for every 1 liter of solution. This should be familiar based on molarity problems that we worked on last week or very recently here, where molarity, when you see that M, is moles per 1 liter. And so that's what we've got here. in our calculation so far. Now, if I stopped right here, I'd know how many moles of sodium hydroxide were used. But what I want to do is get onto the acid. So there's one more step we're going to add on here now, and that's that key step, that 1-to-1 ratio in the equation. In this equation, 1 mole of acid, HNO3, will react with every 1 mole of NaOH that combines with it. So this is a 1-to-1 ratio from the equation up above. If I stop right there, I'll have the number of moles of acid that were in the sample. And we need to stop right there because we can't go any further. If I stop right there, I've got 0.0150 moles of the acid, HNO3, nitric acid. They want molarity. What's the concentration? I need to get concentration here again in moles per liter. So I've got moles. How many liters were we talking about? Well, if I go back in the problem, it tells us there that this particular sample of acid is 35 milliliters. I've kind of got a crowd of stuff here near that information, so I'll try to clean some of this out just so we can kind of get to it. But notice there in the problem, it tells us that there's 35 milliliters of the acid sample, and that's important, 35 milliliters of nitric acid, because that's our volume, right? That's our volume in milliliters that we're going to need to use here at the end. Now, to figure out molarity, I need to have moles per liter. And so to finish this question, I need to take the moles that I've calculated so far and divide those by the number of liters that this sample had for a volume. Well, what is that? 35 milliliters. And we can either do that by moving the decimal over 3 times to get liters, or you can do a little metric system conversion again. 1,000 milliliters is 1 liter. Either way, you're moving your decimal over 3 times. So if you're comfortable doing that, 1, 2, 3 times, move your decimal over 3 times to the left to get to liters. Okay, left to get to liters from milliliters, and that's 0.035 liters. I'm going to bring that up and put it in there as my volume, 0.035 liters of acid. We already used the basis volume earlier in this problem. It was 30 milliliters. We used that right away at the beginning of the problem. Now we need the volume of the acid. So 0.015 moles of HNO3 were found in a volume of 0.035 liters. And if I simply divide that out, I'll have my molarity, moles per liter, moles over liters. And the answer that I should get there is 0.429 m, or moles per liter, and that's my acid concentration. So HNO3, just like that. Okay. So keeping in mind, when they ask us for concentration or molarity, we need to have moles per liter, and those units are very strict. When we're calculating molarity, it's got to be in moles divided by liters. You can't take moles divided by milliliters, because that'll obviously be off by a factor of 1,000, and that'll change your answer a great deal. So that's number 1. Start with the equation. Figure out what that ratio is of acid to base by looking at a balanced equation, and then the rest of it's simply some stoichiometry using 2 molarities, one at the beginning of the problem and one toward the end of the problem where we're solving for the second molarity. Okay. I'm going to work on number 4 with you, and we'll actually come back to number 3 after a bit here. But take a look at number 4. This one's like the pictures that these are the pictures that I used in my earlier video. It's also very similar to the pictures in that were in the Khan Academy video, introducing some of these calculations. And keep in mind, it's the known concentration of HCl is 0.520 moles per liter. You record the following HCl volumes on your burette. Remember, the burette is this tall, thin, kind of graduated cylinder with a dropper on the bottom. It's very precise. You measure the following volumes on your burette: 5.32 milliliters at the beginning. So this is 5.32 milliliters. And remember, on a burette, when we read a burette, we're reading it from the top down. So essentially, 0 is like up here someplace. And it's already been drained down then to 5.32 milliliters. So that's the starting value on the burette. And then after the reaction is done, remember this is our before picture, and this is my after picture, side by side. This isn't 2 different burettes. This is 2 different points in time. And so the second volume afterwards is all the way down here at, it says 29.77. 29.77 milliliters. I should use arrows for these because otherwise it looks kind of like a negative sign. But that's how much was drained out. It started out way up here, and then it was drained all the way down, okay, till it reached this volume way down here. So that's going to help us to figure out how much was used, right? We didn't use 5.32 milliliters. we didn't use 29.77 milliliters. To figure out how much we used, we need to figure out the difference between this point at the beginning and this point at the end. How much is that was drained out? And you simply subtract those two amounts to figure out how much acid was used. And that's the first thing we should do, subtract those two values. How much acid had to be drained to get from initially here 5.32 milliliters down to 29.77. So I'm just going to subtract 29.77 minus 5.32 gives me an answer of 24.45 milliliters of HCl. Remember, I need to know that that's HCl that was in that burette and not the other substance in this question. Right? So those two volumes get used together by subtraction to figure out what the volume of the substance in the burette was that was used. In this case, the substance in the burette is the HCl. So we used 24.45 milliliters of HCl. And we also know its concentration is 0.520 moles per liter. So we know a lot about the acid. We're going to start our problem with the acid because it's the thing that we know about. And then it says you titrated 40 milliliters of NaOH. So that's what's down here. This is 40 milliliters of NaOH. It's down in the flask at the beginning. You titrated it, which is to say you added its opposite to it until it was completely neutralized. And then its opposite would be an acid. So what's the reaction for this equation? We've got HCl being added to NaOH and neutralizing that base to make water and a salt. And it's one that we're familiar with. The Na from the base and the Cl from the acid come together and make NaCl. And this is a 1-to-1 to 1-to-1 reaction. Most importantly, this is a 1-to-1 ratio, just like in the last one. We'll do something where there's a different ratio here in the next couple of problems. All right, so then what? Well, what do we know about and what are we trying to solve? The thing that we know about is the HCl. The thing that we're trying to find is the concentration of the base. Always begin these problems in your calculations with the thing that you already know about, not the thing that you're trying to find. Okay? So start with the thing that we know about. We know the volume of the acid that we used, 24.45 milliliters of HCl, and we know its concentration. Right? We know that 1 liter is 1,000 milliliters of HCl. And again, if you feel comfortable just moving that decimal over 3 times, go ahead and do that, and you're already in liters. You can start your problem out with that. So if you feel okay moving that decimal place instead of doing the metric conversion, save yourself a step and go for it. We know the concentration of that acid is 0.520. That gets dropped in here, 0.520 moles of HCl, right, for every 1 liter of solution. Now, we didn't use a whole liter, but that's the concentration based on moles per 1 liter when it was first made. And then the next step that we'll add on here, and then we'll be moving on to our last part, is the ratio. Okay? So from our equation, 1 mole of HCl reacts with every 1 mole of NaOH. It's a 1-to-1 ratio. So just kind of taking a look before, we'll punch this in our calculator here and get the answer. This comes out to be 0.0127 moles of NaOH. Now we're not quite done, but let's just take a quick rewind here. Where'd we get all these numbers? Right, 24.45 milliliters we started out this problem with. We got that by the subtraction over here using our burette's two values. We took our before and after value and we figured out how much acid must have been drained out and used from that burette. So that's where that came from. The second step in my math here is simply a metric system conversion. So 1 liter is 1,000 milliliters. That's a metric conversion we learned back in grade school. Jot it down, use it all the time. Right? This third part of my math here, 0.520 moles of HCl for every liter, came from right here in the problem. That's what that represents, right? Moles per 1 liter. And then this last part of my calculation so far, this 1-to-1 ratio, came right here out of the balanced equation. So everything that's here in my math so far, came from the information that I was given in the problem. We're not quite done, right? We're very close. We want to know what is the concentration of NaOH. That's molarity, right? That needs to be in moles per liter. We have moles. We figured out 0.0127 moles of the NaOH that they're asking about. Now we just need liters. Right? How many liters of NaOH do we use? Well, we used 40 milliliters. It was right here in the flask, right? We marked that up at the beginning. We used a sample of NaOH that was 40 milliliters. So I could go about that by simply moving my decimal place over here 1, 2, 3 places, and that would give me liters, 0.040 liters. Or you can do a metric system conversion as always, show that calculation if you want to. 40 milliliters. Do that conversion to liters. 1 liter is 1,000 milliliters, and you'd still get 0.040 liters, same value, okay, of NaOH. Right? And then when I divide that out, moles divided by 0.040 liters, my final answer, my final concentration in moles per liter is 0.318 moles per liter of NaOH. It's all about that ratio, right? Moles per liter for our units. And then we're done. That's the concentration of the NaOH. Remember, the thing that we're trying to figure out is down here in this bottom flask. That's the analyte. The analyte needs to be studied. The analyte needs to be analyzed and calculated. Something about it needs to be calculated. And then up here in the flask is the, or in the, I'm sorry, in the burette is the thing that we know everything about. We know its concentration, and we're about to measure very precisely how much volume we use of that. And that's that titrant. It's doing the action, coming in and neutralizing the species down below in the flask, and we know everything about the titrant. That's our fully known participant. It's the analyte that we're trying to learn more about, as we did there. All right, let's take a look at number 6. I chose number 6 because I want to show you a question or two where the ratio is a little different than that 1-to-1 ratio that we've seen so far. So here we've got HCl, that's our acid. And we've got a base here of strontium hydroxide. So here's SrOH2. Now when those combine, it's still an acid and a base, so we're still going to get water. And we're still going to get a salt. We're going to take the strontium here from our base with its 2+ charge. And we're going to put that with chloride from the acid with its 1- charge. And when those get together, we get a SrCl2 like that. But most importantly, the way to kind of recognize the ratio here is, remember, acids and bases neutralize because the positive hydrogens from the acid and the OH negative ones from the base get together. And when this acid and this base get together, the base brings 2 OHs to the reaction that's taking place, while the acid only brings 1 hydrogen here. We can see in the equation that there's 1 hydrogen, but there's 2 OHs. So for those 2 substances to work together, we can't just put them together 1-to-1. It's going to take 2 of these acids for every 1 of the bases. And that way, if you think about it, the 2 hydrogens from this 2 acids here will combine with the 2 hydroxides, there are 2 of them, the 2 hydroxides from the base, to make 2 H2Os. So we'd actually finish balancing our equation with a 2 there and a 1 there. That's the ratio that's going to be important. The hydrogens and the hydroxides have to work out together. They have to balance out and neutralize each other evenly, otherwise the reaction doesn't come out quite right. And so to get that to happen in our equation here, we need to have 2 HCl's for every 1 strontium hydroxide. Sort of think about it as if that base is sort of double powered or double strength. And because the base is double strength with those 2 OH groups, it'll take twice as many molecules or moles of the acid for them to work together. And so that's why it's a 2-to-1 ratio. That is a vital piece of this question. We have a 2-to-1 ratio of acid HCl to base strontium hydroxide SrOH2. And that 2-to-1 ratio is going to show up in the stoichiometry and be pretty important to this question. Now, what do we know about what are we trying to solve? We're trying to solve the HCl. We'll calculate the molarity of HCl. So we're not going to start with that. We're going to start with a thing that we know about. And what we know about the strontium hydroxide is its volume and its strength. All right, so we'll start with the volume as we did before, 15.5 milliliters of our strontium hydroxide. If you want to do your quick metric conversion, or just move the decimal point, whichever one you prefer, that's going to get us to liters, if we simply move the decimal over 3 times. And then we know the molarity there is given as 0.400 moles of strontium hydroxide for every 1 liter. Right? That's what that 0.400 molarity tells us. 0.400 moles per 1 liter of solution. And then one more step on the end of that, and this is that key ratio step. According to my equation, right up here, when we balanced it out, right, there will be 2 moles of HCl reacting for every 1 mole of strontium hydroxide. If we look back at the problems that we've done together so far on this page, they've both been 1-to-1 reactions, and there are many, many 1-to-1 reactions of acids with bases, but there are commonly other ratios like this 2-to-1 ratio. So make sure to be paying attention to that and writing a balanced equation that matches with the formulas for the acids and the bases. Now, what does that come out to be? I calculated that out at 0.0124 moles. And moles of what? Moles of HCl. Now that makes sense because they want the molarity of the HCl. Here's our eventual question. Calculate the molarity of the HCl solution. And so for molarity, we need moles over liters. How much HCl did we use? It says here in the problem that we used 25 milliliters of the solution. And that's a number that we haven't used yet. So remember, 25 milliliters, move the decimal over 3 times, or do the 1 liter is equal to 1,000 milliliters conversion. Move that decimal over 3 times, and we'd be talking about a sample of 0.0250 liters of HCl. If I divide that out, I'll have my concentration of the acid, 0.0124 moles, divided by 0.0250 liters, and that's right around half, specifically 0.496 moles per liter HCl. Not much different about that problem, but the one thing that was different was this 2-to-1 ratio here that we see between the acid and the base. And that 2-to-1 ratio matters because if we treated it as 1-to-1, then obviously we would have half as many moles, and we would have a molarity that's half as much, and we'd be off by a factor of 50%, which is a pretty big deal, right? Can't just blow that off. You have to take that into consideration. All right, one more question. Let's take a look at number 3. Number 3, again, has a ratio that's not 1-to-1, so just want to make sure that we see one that kind of goes the other way. And I won't spend as much time talking about that on this one because you've kind of already seen it, but our equation, H2SO3, is our acid. Our base is NaOH. This is a case where the acid is sort of double in strength because it has 2 hydrogens here, while the base only has 1 OH group. And that little OH group there is what kind of decides the balance, right, between the acid and the base. Because it takes an OH for every H for the reaction to work and produce the water that it's going to produce, and then the other substance would be our Na2SO3, we're going to need, in order to balance that equation, we're going to need 2 units of base for every 1 mole of acid, and that'll make us 2 waters and 1 of our salt. This ratio then of 1-to-2 is what will give us our step there that connects the moles of each to each other. All right, so what are we trying to find? We're trying to find the NaOH. What's the molarity of the NaOH? Which means we're going to start with the other guy. We're going to start with the acid in this case. So we're going to start with 10 milliliters of our acid. We'll do our metric conversion, 1 liter is 1,000 milliliters. Or just move that decimal if you're comfortable. And then we need molarity. In this question, we've got a concentration for our acid here given at 0.100 moles of H2SO3 for every 1 liter of solution. There's our molarity, right? And then that ratio comes into play. In this example, there's 1 mole of H2SO3 in our equation for every 2 moles of the base. Remember, the acid is double strength, so it will take twice the amount of base to neutralize it as a result. When I do my calculations here, all my units cancel out, and I'll have my moles of NaOH. That comes out to be 0.002 moles of NaOH. We need molarity, so we need moles over liters. How much of the NaOH do we use? Back up here in the problem again, we used 19.5 milliliters of the NaOH, and that 19.5 milliliters, we're going to move that decimal over 3 times to get to liters. So 1, 2, 3. We're going to need to put a 0.0 in front and divide our moles by liters, 0.0195 liters. If I go to my calculator, figure out what that concentration is going to be, my answer comes out at the end to be 0.103 moles per liter of NaOH. And there's my concentration of the base as asked for in the question. So the steps on all these are very much the same. Start with an equation. Make sure to find out what the balanced ratio will be, whether it's a 1-to-1 or a 2 to 1 or a 3 to 1. That's about as complicated as they would ever get. And on the product side, it's always a water and salt. The question is, how many acids and bases will it take for those to work out together and balance the equation? All right, I'm going to leave the rest of the questions on this assignment to you. There's really not too much to the problems that are different than the ones that you've already seen. Some of them are 1-to-1 ratios, some are not, so be on the lookout for those. At the very end of the assignment, there are a couple of questions that are kind of just bringing the concepts of titrations back around again and seeing what you come up with for an answer on 11 and 12. But for all the rest of them, the calculations are pretty much like what you've already seen in our examples together. Thanks for watching. Get through those and get your assignment turned in as your instructions will tell you. You should have a couple of opportunities between now and then, though, for office hours with me. If you have questions on the assignment, drop in or shoot me an email if you have to, and I'll try to help you out best I can. All right? Thanks for listening, and we'll talk to you soon.